Hello, everyone. In this lecture, we want to talk about group and field uh, as we need this concept again to understand growth section. Okay, so what is a group? Uh, in mathematics, a group like G consists of different elements, is defined with a binary operation that satisfy four following operations. So when we say binary operation, this means that the operation is executed between two elements of the group. Okay, the first property is called closure, and it says that if we choose two elements of this set and then compute the result of the operation between that two elements, the result would be a member of the group again. So let's uh, review these properties with an example. We want to see that if the set of integers uh, under addition operation is a group or not. Okay, the operation that we choose here is addition, right? So instead of the circle, we want to put everywhere addition. So the first property was closure. If we choose two elements from this set, which is set of integers, so this is the set of all numbers that we want to pick and work on them. If we choose any two elements from this set, the result of the addition of any two elements is also another member in the set of integers, right? And the reason that we put add addition here, as I said, is that the operation is addition in this example. We will later work with the multiplication example also. Okay, so then this set and the operation is passing the first property, which is closure. The second property is identity element. So the identity element says that there should be an element like I in the set such that when you compute the result of operation between any element of the set and the identity, the result should not change and should be equal the original chosen elements. So in the exemplified a group, the identity element should be an element like I, that when you pick any element from the set of Z, so then result should not change and should be equal to A, right? And yeah, the identity element here is I. Yeah, I equals to 0, right? Why? Because if you pick any number from the set of integer and then add it by 0, so then the result equals to the original element. For instance, if you pick 2 and then add it by 0, it is equal by 0 plus 2, and it is equal to 0, right? If you put here 1, so then the result again would be 0. Sorry, it is 2. Yeah. And if you pick 1, then the result equals to 1, right? So this means that you can pick any number from the set of integers, add it by 0, and then the result is the chosen number. Okay, so the identity element exists in this set. So the second property is passed. The second property is the inverse element. And it says that if you pick any random element from the set, there should be an inverse element in that set that if you do the operation between the chosen element and its inverse, so then the result should be equal to I, the identity element that we found in previous property, right? So in our exemplified group, since the identity element is 0, so then we need to find the inverse value in a way that the value plus its inverse equals to 0. Okay? So, for instance, suppose that we have chosen a equal to 3, right? So then 3 plus the inverse of a should be equals to 0, right? So is there exist such an inverse in the set or not? If we check the set of integers, we can find minus 3, and 3 plus minus 3 equals to 0, right? So then there exists an inverse. So inverse here doesn't mean 1 divided by the value. Inverse here means that a value that when you add by the original value, the result should be equal to 0. So the inverse of 3 here is minus 3. And if you pick a equals to like minus 4, so then minus 4 plus inverse of a should be equals to 0. Can we find an inverse for minus 4 in a way that minus 4 plus the inverse equals to 0? Yeah, so the inverse equals to 4 here. Minus 4 plus 4 equals to 0. So then we can say that for any element belong to this set of integer, we have an inverse, right? Now we want to discuss the final property, and that is associativity. It says that if you pick 3 elements from the group and you do the operation over the first 2 elements and then by the third, the result should be equal if you do the operation between the second and the third element and then do the operation with the first element. Okay, for instance, if we pick A equals to 2, B equals to 3, and C equals to 4, then 2 plus 3 plus 4 should be equal 2 plus 3 plus 4. So this is 5, and this is 7, and the left side equals to 9, and the right side equals to 9, right? So the associativity property also is correct on the chosen set. Okay, since the chosen set of integer under addition operation satisfy the 4 property, so then we can say that, okay, this is a correct group. So this is this set of, let me clean this. Yeah, the set of integers under the addition operation is an additive group. So additive group means that the operation that we have chosen was addition. Okay, now we want to review another example. So the second example is set of integers under multiplication operation. We want to check that if this is also a group or not. Okay, so the first property is closure. If we choose any 2 elements from this set of integer, and then compute their multiplication, if the result of this multiplication is also again an element of integers, Yeah. So for instance, if you pick 2 and b equals to 3, 2 multiplied 3 is 6, and that's an element of integers, right? So the identity element says that if there is an identity value that when you multiply any element by the identity, the result equals to original chosen element or not. And yeah, so the identity element here is 1, right? Because if you, for instance, choose a equals to 3, so then 3 multiplied by I should be equals to I multiplied by 3 and equals to 3. So what is the value of I? So that's definitely 1. So then the identity element for this group is 1, while the identity elements in the previous group was 0, right? Okay. Now the third property, the inverse elements. So if there, for any chosen element of Z, if there is any inverse value that when you multiply A and the inverse, the result equals to 1 or not. For instance, if I equals to 3, so then if 3 multiplied by A minus 1 equals to 1. So can you find an element in the set of integer that when you put here, the result of this multiplication equals to 1? So it seems that there is no element, right? Because if I put 1 over 3, so then 3 multiplied by 1 over 3 equals to 1. But 1 over 3 is not an element of this set of integer, right? So then there is no a set of an inverse value inside the set of integers. So then the third property is not satisfied. So then we say that this is not a group. Okay, so let's discuss the third. Let's discuss the third one, the third example. Okay, now we want to discuss the set of integer. Just start from 1 to 100. So to show this set, we use Z, which means that we have a set of integer sub 101, which shows that the value starts from 0 to 100, like f of 101. In previous lecture, we discussed that this set starts from 0 and then till 100, right? But this star value here, this star sign here shows that the set does not consist of 0. Okay, now we want to see that if the z star sub 101, which is the set of consists of 1, 2, 3 till 100, under the multiplication operation is a group or not? Okay, the first property says that and yeah, by the way, in this group, we also consider the computation in modular arithmetic and mod 101, right? We compute all the computation in mod 101. Okay, so if A and B are element of this set, so this should be Z star sub 101, not Z. So then the result of the operation also should be an element of this Z star sub 101. Okay, so if this is correct or not, so suppose that A equals to like 50 and B equals to 60, right? So then A plus B equals to 110. And we said that we should do the computation on mod 101, right? Which is equal to 9 in mod 101, right? And 9 is an element of this group, this set. So then the first property is passed. The second property says that if there is an identity element that A multiplied by I equals to A or not. So let's exemplify another instance. For instance, if A equals to 3, then A multiplied by I should be equals to I multiplied by A, which is 3, and then equals to 3, right? So if there is an element inside this set that I multiply 3 equals to 3, yeah, and that is 1. The identity element for this group is 1, right? Okay, the inverse element. For any element in this set, which was the set of stars of 101, there exists an inverse value in this set that the multiplication between the value and the inverse should be equal to 1. For instance, if the value of A equal to 34, then 34 multiplied by the inverse should be equal to 1, right? So if you use the website, or if you remember from the previous lecture, we discussed that the inverse of 34 in mod 101 was equal to 3, right? So if you do not remember, you can use the website to compute the inverse. And yeah, so 34 multiplied by 3 equals to 102, and 102 mod 101 equals to 1. So this is correct. Every element has an inverse value. And the fourth property also is satisfied in this group. So then we can say that, okay, this group also, this chosen group is also a valid group, right? So this is a valid group right here. Okay. This is a multiplicative group, and we say multiplicative group because the operation that we have chosen is multiplication. Yeah, as we already discussed, the S star here means that we exclude 0 from this set. Okay, now we have two sets here, but the second one, this is not a valid set, right? We have just two sets here. Okay, so now we want to talk about a generator of a group. When we have a group, each group has at least one generator. And generator is an element belongs to the group that if it combined by itself using the group operation, it can generate other elements of the group. So this means that if your group is an additive group, this means that, and G is the generator, so you have G as the original element, and then you can add G by itself, or you can add G multiple times or by itself, or finally, you can multiply Gn times by n. So this n could be a negative, a positive, or a zero. Okay. Yeah, and also in the multiplicative group, the G value should be multiplied to itself. So by computing G and G to the power of 2, G to the power of 3, and then G to the power of n, you should be able to generate other elements in the group. So there is no simple or straightforward algorithm to find the generator of a group, but there are multiple regulations that allows you find generators sooner. But we don't want to discuss those algorithms because we don't want to go very deep into the generator of a group. So just I want to give you a hint to understand what is a generator without understanding what is the protocol to find that. Okay, so we discussed already two exemplified of groups, and now we want to compute or discuss their generators. For the first group, the set of integer under addition multiplication, we see that the value of n, the value of 1, which is here, is the generator of this group. Why? Because now we have an additive group. So since this is the additive group, we need to follow this formula. So this means that by using n multiplied by j, so here j equals to 1, right? The generator is 1. So this means that n multiplied by 1. By using n multiplied 1, you should be able to generate all the elements of the set of integer, all the elements like 2, 3, 4, and also the negative values. So we can do that because if you replace the value of n by a positive integer, negative integer, or a 0, so then you can generate the other elements of the set of integer. So then we say that G equals to 1 is a generator of this group. So the second generator of this group is -1, because if you multiply n by -1 and then replace the value of n by negative integers, positive integers, and 0, you can generate other elements in the set of integers, the chosen group, right? For instance, if you put n equals to 2, then n multiplied by -1 should be equals to -2, right? So the -2 is generated here. If you want to generate 3, for example, you put n equals to -3, and then -3 multiplied by -1 equals to 3. Okay, so now we could generate other members of the group with -1. So then we can see that both 1 and -1 are the generator of this group. And there is no other generator for this group. Okay, what about the, for instance, we want to see that the value of 2, this is not a generator. Why? Because if you want to put G equals to 2, let's say G equals to 2, now we want to generate other members of the group. by n multiplied by g, or 2n, right? If you put a positive integer, a negative integer, or 0 instead of n, you cannot generate a value like 3, right? So if you put any positive integer, negative integer, or 0, you cannot generate value of 3. So then the number of 3, which is element of the set of integer, cannot generated by 2. So then we say that, okay, the value of 2 is not a generator of this group. Okay, this group so has just two generator, 1 and -1. Okay, so let's discuss the other group, the second group that we exemplified already. So we discussed the set of integers mod 101 and a star which exclude 0. So also discussed that this value should be updated by 101. Okay, anyway, so this is a multiplicative group, right? To find the generator of such a multiplicative group, we need to follow this formula. So we say that if a value claims that I'm a generator, so it should be multiplied to itself n times, and could be 0, positive integer, or negative integer, and then generate other members of the group. For instance, we say that the value of 2 is a generator of this group because the 2 to the power of n, for instance, if the value of n equals to 0, then 2 to the power of 0 equals to 1, right? So then the value of 1 is generated. 2 to the power of 1 equals to 2, which is the generator itself, right? 2 to the power of 2 equals to 4, and then 2 to the power of 3 equals to 8. And then if you increase the value of n to 7, 2 to the power of 7 equals to 128, but we need to compute the computation over mod 101, so it is 27, which is another element from the group, right? So if you follow this step for other values for n, you can generate all the members of this step. So therefore, the value of 2 is a generator of this group. For instance, the value of 1 is not a generator for this one. So 1 was the generator for the previous group, but it is not the generator for this group because 1 to the power of n, if you put any value, positive, negative integer for n, you just be able to generate 1. You cannot generate 2, 3, 4 till 100, right? So then 1 is not the generator of this group. So the other generators of this group are 3, 7, 8, 11, and some other elements as the generator. Again, we don't want to discuss the algorithm that we find the generator. We just want to understand what is the generator with some examples. Okay, now we want to discuss field. A field is a set of numbers that we could do addition, subtraction, multiplication, and division, excluding divide by 0. And then the result exists in the set. So there is a difference between the field and the group, right? In the group, we had some specific operation, and we expect that the results under that specific operation exist in the group. But in the field, we expect that the result over the 4 main operation exist in the field. So that's the difference. Now we want to exemplify some fields. So the set of real numbers, if that's a field or not. So suppose that we want to pick two numbers from the set of integer, and then we compute add of that two numbers. If the result exists in the set of real numbers, yeah. What about subtract? Again, the result would be inside the real numbers, right? And the multiplication and also division. So if you divide two real number to each other, the result would be again another real number. So then the set of real number is a field. Okay, so if set of integers, this is a field or not. We already discussed the set of integer under multiplication operation, which is not a group, but under addition operation is a group, right? We discussed already. Now we want to see that if the set of integers uh, is a field or not. So if you pick two values from the set of integer and then add them to each other, if the result exists in the set of integers, yeah. And if you do for the subtraction again, yeah. And if you multiply two integer values, so then the result would be an integer value, right? But for division, if you pick two integer value like 2 and 3, and then divide 2 by 3, so then uh, 2 divided by 3, it is not an integer, right? So then this set of number, this is not a field because the result of division is not an element in this set. And now we want to discuss another important field, and this field is important for us because in next lecture we will do many computation over this field. And this is the field of uh, f sub 101, which consists of 0 to till 100. And the computation in this field should be done in the mod 101. So if you add two elements from this set, so then the result again would be an element of these two sets, right? For instance, if you add 60 plus 70, the result equals to 130, and then this is equals to 19, right? In mod 101. We compute all of the computation over in mod 101. So then 19 is an element of this group. So for the addition, this is correct. For subtraction, so let's say 60 minus 70, we pick two values, 60 and 70, from this set, and this is equals to minus 10. And you remember that we can add minus 10 by 101 to compute the uh, mod values. So, and this is 91. Again, this is an element of this set. For multiplication, if you multiply 60 and 70, you can use the website again. So let's see in our website. So here, modular arithmetic, 101. It is 16, right? So this is 60. Okay. Oops, sorry. What was the value? 16. Okay. So this is again an element. belong to the set. So then this is correct. And then the division, 60 over 50 over 70. We discussed in previous lecture that it should be 60 should be multiplied by the inverse of 70, right? And in our website, we have a tool that you can compute the inverse of 70 in mod 101, which is 13, right? So then we have 13 here. $60 over 70 equals to 60 multiplied by inverse of the 17, which is 13. And then you multiply this value again and compute mod, and you will see that the result is an element inside the set. So then the result of all this for computation exists in the set, and this is our very important field that we will do many computation over in this field in next lectures. Okay, so other than field, we want to discuss extension field. So extension field is generated or made by the elements of the field. So for instance, we want to compute an extension field using the field F sub 101. So the extension field says that it consists of all elements in form of A plus BI, when A and B are elements in 101. So this A and B could be 0. So for instance, if A and B, both of them equals to 0, so then the element would be 0. If A equals to 1 and B equals to 0, so then we have 1. So if A equals to 0 and B equals to 1, we have I. And if A and B, both of them are 100, we have 100 plus 100i. So A is called the real part and B is called the imaginary part of the element in the extension field. So we see that the F sub 101 has 101 elements and F sub 101 to the power of 2 has 101 to the power of 2. So that's the reason we say extended field. So the field is extended from F sub 101 into F sub 101 squares. Okay, so we already discussed that F sub 101 is a field, right? How we discuss that? We compute the addition, subtraction, and multiplication, and we have shown that the result of all of the four computation is again an element into F sub 101. So now we discuss extension field, and we define what is the extension field, but we want to prove that this is also a field. So this is the defined extension field, and now we want to see if the result of these four computation exists in this field or not. Okay. To do the computation over extension field, we need to define some new concept, and that is irreducible polynomial. Okay, what is an irreducible polynomial? First, we want to say that, okay, if we are working in F sub 101, if sub 101 equals to our field, which consists of 0 and 1 and 2 until 100. So then f sub I and x means that different polynomials that their coefficient are element of f sub 101. For instance, polynomial x to the power of 3 plus 5x2 plus 16x plus 100 is such a polynomial because all the elements, they are values from this field. So here x to the power of 2 minus 4, this is like x to the power of 2 plus 96, right? Because minus 2 mod 101 equals to 96. So x to the power of 2 minus 4 belongs to the list of all polynomial on this field because that equals to x to the power of 2 plus 96. So here we can divide this polynomial on of degree 2 into some other polynomials, and then we say that this here our polynomial is reducible. So we want to discuss in general to see if a polynomial is irreducible or not. So when we say a polynomial is reducible or not, so this means that you can divide the polynomial in multiplication of different roots when the roots are elements of the f sub 101. So the formula says that if you define the polynomial in form of a x to the power of 2 plus bx plus c, and this is just for the polynomial of degree 3. We don't want to discuss the polynomial of degree 3 or higher than degree 3, right? So this is just for polynomial of degree 2, right? Sorry, I said that I told you, I thought that I said polynomial of degree 3. That was wrong. So here we just want to discuss polynomials of degree 2. Okay, if the polynomial is defined in form of ax to the power of 2 plus bx plus c, we define a term called delta, which is b to the power of 2 minus 4c. And then in the finite field, you need to compute delta to the power of p minus 1 over 2. And then if delta equals to 1, your polynomial could be reducible by two distinct non-zero roots, like this polynomial, right? So here, in this example, this polynomial, it is reducible by two roots. And if you compute this value, you will see that the value for this exemplified polynomial equals to 1. So if this value, delta to the power of p minus 1 over 2 equals to minus 1, so then the polynomial has dozen root, or it is called irreducible polynomial. So in reducible polynomial of degree 2 is a polynomial that satisfies this equality. And then if the delta to the power of p minus 1 over 2 equals to 0, so then polynomial has one root. Okay, we already exemplified this polynomial that has two roots, and now we want to exemplify another polynomial that has no roots. And this is our example, x to the power of 2 plus 97x plus 2. And if you compute delta and then compute mod 101, you will see delta equals to 8 here. And then delta to the power of p minus 1, P equals to 101, right? Over 2 equals to 8 to the power of 50, and that is equals to minus 1. If you do the computation, you will see this value equals to minus 1. And since this is minus 1, this polynomial doesn't have roots, or this is an irreducible polynomial. Okay, now you may ask that what's the benefit of definition of reducible and irreducible polynomials? Okay, we already discussed that the extension field is a field, and we want to do the computation over the extension field to see that if the result is an element from the extension field or not. And if yes, we conclude that this is really a field. After defining irreducible polynomial, now we want to go back and compute the for operation in the extension field. Okay, we said already that our field is f sub 101, and our extension field is f sub 101 squares. Okay, to do the computation, you need to find an irreducible polynomial of degree 2, and we found that polynomial already in previous slide, right? It was x to the power of 2 plus 97 plus x plus 2. And the next step says that you need to replace the value of x by I in the polynomial. Then I to the power of 2 plus 97i plus 2 equals to 0. And then by here, you compute I to the power of 2, which is equals to minus 7 I minus 2, and when you compute minus 97 in mod 101, it is equals to 4, and if you compute minus 2, the result equals to 99 in mod 101. Okay, what's the benefit of computing I to the power of 2 from the irreducible polynomial? You will see later. Okay, so now we want to discuss addition. So addition of two elements from the extension field like a plus bi and c plus di, to add these two values, you will add the real part to each other and then the imaginary part to each other. For instance, 2 plus 3i plus 1 plus 2i, you will add the two real part to each other. 2 plus 1 equals to 3, and 3 plus 2 equals to 5i. Okay, so in our website, we have a part to compute the computation over the extension field. So here, this is the extension field, and for the addition, so here in the website, you also see that I to the power of 2 equals to 4i plus 99. So this is not computation for any extension field. This is just for the specific extension field that we already discussed in the PowerPoint. So for instance, if you have 43 and 4, and then 3 and 12, so then addition of these two elements of the extension field equals to 56 plus 16i. So you will have the same thing for the subtraction. So after that, we want to discuss the multiplication. To do the multiplication of two elements in the extension field, the elements are a plus bi and c plus di. You will multiply a by both the real and imaginary part, and then the second one, the bi, by the c and di. And then you will have the final result in this form. But here, okay, so let's do with an example. 2 plus 3i multiplied by 1 plus 2i. So if you do the multiplication, you will see this result, 2 plus 4i plus 3i plus 6i2. And this would be 7i, right? 2 plus 7i plus 6 to the power of i2, right? So this is the result of multiplication of these two members. But if this result is a member of the extension field or not. So the extension field consists of just the real and imaginary part, the values like 1 plus I, 2 plus 3i, something like that. There is no term of I to the power of 2 in the extension field, right? So here we see that the result of addition, this is an element of the extension field, but the result of the multiplication, this is not an element of the extension field because we have an extra I to the power of 2. And that's the reason we already compute the value of I to the power of 2 equals to 4i plus 99. So now we replace the value of I to the power of 2 by 4i plus 99, and the final value would be this. And this is also an element in the extension field, right? So all the discussion about reducible and irreducible, and then computing I to the power of 2, because we need to replace something by the value of I to the power of 2. So you may have some question about why we replace I to the power of 2 using an irreducible polynomial of degree 2, and why we do not replace it by an reducible polynomial. So those are so many details that we don't want to discuss, right? We just understood how compute I to the power of 2 and then replace the I to the power of 2 with that value. Okay, so the other computation is exponentiation. So exponentiation also is just repeating the multiplication, right? That is not more than the multiplication. And also subtraction is equals to addition. So we discussed addition. Subtraction was similar to addition. We discussed multiplication. Now we discuss the final one, the division, right? So we already discussed the 3. Now we discuss division. Okay, to do the division, we need to compute the inversion, right? If you compute the inversion of a value, then you can compute division, right? For instance, suppose that you want to compute division of like 2 plus 3i over 32 plus 25i, right? So we already discussed that this is equals to 2 plus 33i multiply by the inverse of 32 plus 25i. So that's the reason we need to compute this value. And we already we discussed in previous lecture how to compute the inverse of a value, and that was by the Fermat theorem. It was equals to 100 p to the power of 2 p to the power of p minus 2. Okay, so using that formula, you will reach this value, and using the multiplication, which is again actually multiple multiplication, so we'll finally compute the inverse. So if you replace the value of inverse here by 47 plus 24i, then you will multiply these two values to each other using what we discussed already from here, and then replace the value I to the power of 2 by 4i plus 99, and then you will compute the final division, and you will see that the result is an element from the extension field. Okay, so in our website, we also again have exponentiation and also the inversion. So let's work with our website again. So we have exponentiation here. For instance, we want to compute 3 plus 4i to the power of 5. It is equal to this value. We want to multiply these two three values, and then the result is computed here. And also, if you want to do some division, you need to compute the inverse, and this part allows you to compute the inverse, right? The inverse of 5 plus 23i equals to 72 plus 10i. Okay. Okay. So now we want to discuss the final part, which is if we want to ensure that this inverse value is computed correctly or not, right? We already discussed the inverse value is a value that when you compute the multiplication of the value and the inverse, the result equals to 1. So if you compute the inverse, which is 47 plus 24i, and then multiply the value by 32 plus 25, you finally reach to the value of 1. So you can check this by the website, or you can compute this multiplication manual, and then you see that this value equals to 1, so then the inverse is computed correctly. Okay, so other than the extension field of the power of 2, we have extra powers for the extension field, like f sub p to the power of 3 and something like that. We do not want to discuss those more higher degrees of the extension field. It's good to know that we have some other extension field of higher degrees also. Okay, for our next discussion, we just need this field f sub 101 and f sub 101 squared. And also we need to know how the addition, subtraction, multiplication, division, inversion, they are computed in this field and the extension field. Okay, thank you. We will discuss the elliptic curve cryptography in the next lecture.